Hello everyone, it's me again. Once again, sincere thanks for your strong support. Today, I'd like to embark on a new topic, which is the characteristics of components at radio frequency. For this series of discussion, I'm going to discuss the various components, like for example, wire, resistor, inductor, and capacitor. I'm going to discuss on their characteristics, how they actually behave at a higher frequency, such as radio frequency. For this video, I'm going to concentrate on wire. For wire, I will have part 1 and also part 2. Part 1 mainly will discuss on the characteristics of the wire at a higher frequency. As for part 2, I'm going to show you an example. How can we do a little calculation to determine whether this wire is suitable to use at a high frequency, such as radio frequency. For example, at this particular part 2 series, I'm going to show it to you the size of the wire or the diameter of the wire and also the length actually contribute to determine whether they are suitable to perform at higher frequency. This is my email. If you have any question regards on today's discussion, please drop me an email. Before I continue, I'd like to urge you guys to support this channel by pressing the like and subscribe button. Please also turn on your notification bell in order to receive more information from this channel. Once again, sincere thanks for your strong support. Like I mentioned earlier on, the part 1 series discussion, I will concentrate on wire. Over here, I'm going to discuss the behavior of wire at a higher frequency, such as radio frequency. A wire can be used for an interconnect from one point to another point. Typically, we'll be using this wire to connect one point to another point. So this is what it means. For example, the wire can be a jumper wire. The jumper wire, like what you mentioned here, is basically to connect one point to another point. We also will provide power for the device using wire. Okay, for example, when we actually charge our mobile phone, okay, we actually connect them to the power supply. The power supply actually came with the cable. The cable can also behave like a wire. We also have PCB copper thread. Okay, for example, in a PCB board, we have all the copper thread running around. So basically, this copper thread can be also mimic like a wire. I'm going to explain to you all the 5 parameters that will determine the parameters of wire, whether they are suitable to use at high frequency or not. Okay, firstly, okay, basically, we would like to know the type of wire. Typically, the material that we use for wire, they are actually mainly copper, but we actually prefer to coat them with tin or silver in order to have a better solderability conductivity, which means that, okay, with copper, okay, I actually want to coat them with tin or silver so that they will be much more easier to solder with a better conductivity. As for the type of wire, mainly there will be solid conductor and multi-strand conductor. Over this diagram here, you can see that this is basically a solid conductor. The wire is basically one solid part. As for here, you can see that this is multi-strand conductor. Okay, you can see that they are made up of many strands of conductor like copper to make into a wire. Next, okay, I'm going to discuss on wire size. How can we determine the wire size is by this standard, which is called the American wire gauge. Okay, over here, okay, which is shown on the table on the next slide, the diameter of the wire can actually present in these AWG tables. The AWG numbers is inverse proportional to the wire diameter, okay, which means that when I actually increase my AWG, my wire diameter actually reduce. Okay, so they have a inverse relationship between AWG and the wire diameter. Okay, over here you can see the equivalent circuit of the wire. Okay, so this is wire. They actually behave like a R in series with L. Okay, so this is the equivalent circuit of wire at a higher frequency. As I mentioned earlier on, this is the table for AWG. Okay, so from here you can see that AWG actually increase. As I illustrate earlier on, when AWG increase, you can see over here the diameter actually reduce. Okay, so this is basically the column for the diameter of the wire. Over this column here is basically the wire in terms of mils. Over this column here is the wire diameter in terms of millimeter. So like I illustrated earlier on, you can see that when AWG increase, the diameter actually reduce. So they have an inverse proportional relationship. On this column here, okay, we can actually see the resistance. Okay, for example, over this column here, you can see that the resistance is actually measured with 1,000 feet of wire, for example. Over here, you can say that, okay, the wire has 5.488 ohms per kilometer. Okay, so this is how can we describe the wire characteristics using this AWG table. Next, I'm going to discuss on high frequency resistance, okay, which is also known as skin effect. Okay, at low frequency, okay, which means that like a DC, etc., the charge carrier is evenly distributed throughout the cross section of a wire. So you can see this is a cross section view of the wire. So at a very low frequency or DC, you can see that the charge actually evenly distribute overall on the cross section view of the wire. You can see over here. However, at high frequency, there is an increase of magnetic field at the center of the conductor. Okay, you can see from here. Okay, at higher frequency, you can actually see that there's an increase of magnetic field over this center of the conductor. Okay, this actually present an impedance to the charge carrier. Okay, which means that they has a higher impedance. Okay, this will discourage, okay, the current to flow at the center of the conductor. Okay, so this will increase the current density around the edge of the conductor, which is known as skin effect. Okay, so this is what we have learned during our school day. Okay, we know that at higher frequency, the current is not going to be evenly distributed. Okay, because at the center of the conductor, okay, we actually have an increase of magnetic field. Okay, this actually present a higher impedance to discourage the charge to flow at the center of the conductor. Hence, okay, the charge actually prefer to flow on the edge of the conductor. And this is what we know as skin effect. Skin depth. Okay, the depth into the conductor at which the charge carrier current density fall 1/E or 36% of its values along the surface is known as the skin depth. Okay, so later on, let me illustrate a diagram to explain what is skin depth here. So skin depth is a function of frequency, permeability, and also the conductivity of the medium. Okay, so this is what we have discussed just now. Okay, so because of higher magnetic field, okay, the charges don't actually prefer to flow at the center of the conductor. They actually prefer to flow at the edge of the conductor. So this is what it means. So for example, I can easily find my area under this whole this white color area here. Okay, so I also can find the whole area, okay, using this pi r squared. So in order to find the skin depth area, okay, I can actually use this area under the 2 minus area under the 1. I can also rearrange the formula that look like this. So this actually calculate, okay, the skin depth area, which is calculate the shaded region here. Okay, so this is what it means over here. Okay, so this is what I meant about this skin depth. Okay, when the charge current actually fall under either 1/E or 37% here. Okay, so this is what is also known as skin depth. Okay, so this is the 4th parameters that I discussed, which is the skin depth. Let's move on. Skin depth may be expressed by this equation. Okay, so later on, okay, on the part 2 series, I will use this equation to calculate the skin depth. But from this equation here, you can see that skin depth is actually a relationship with frequency. Okay, so this radian is actually 2 pi f. Okay, it's also a relationship with the permeability of the material and also the conductivity of the material. So over here, you can see that the skin depth is actually depend on frequency, permeability, and also the conductivity. Okay, any increase of that number, I actually reduce my skin depth. Okay, so this table here shows a few of the conductivity and also the permeability, okay, in terms of the number. Okay, you can see the number here. So later on during the part 2 series, okay, I will make use of all these table to do some calculation. Okay, let's take a look on this here. So the skin depth, okay, is actually controlled, like for example, the conductivity. Okay, so when I actually reduce my conductivity, okay, my skin depth actually increase. Can you see here? When this is actually reduced, okay, I actually have a bigger skin depth. Okay, when I actually have this, the area under the AC will also increase. And this is actually governed by this equation here. So from here, you can see that when I actually increase my area under AC here, okay, I can actually see over here. Okay, let me move this side. I can see over here, my RAC also will be reducing, okay, because I actually increase here. So when I actually increase here, my RAC actually reduce. Okay, so don't worry about this. Okay, on the part 2 series, I will have a better discussion on this. Next, let's move on to the inductor of a straight wire. Okay, every wire has self-inductance when current pass through it. At low frequency, the self-inductance of a short length of wire is insignificant. Okay, and the inductance value can be calculated as shown by this equation here. So from this equation, you can see that it's a function of the length of the wire and also the diameter of the wire. Okay, so this is a relationship we can see from here. Okay, this show that the inductance of a given wire depend on its diameter and also the length. And basically, they can be minimized by making the diameter larger. Okay, so when I actually have a larger diameter, okay, so which means that a larger diameter, I actually reduce my inductor. And also, if I make the length shorter, so this is shorter, my inductor value also will be smaller. Okay, this is basically the idea here. So the larger the diameter, the lesser the flux linkage outside the wire, and hence the lesser the inductor. Okay, so I guess I have come to the end of this part 1 series discussion. As I share with you on the part 2, okay, I'm going to share with you an example how to calculate the wire to determine whether is it possible to work at a particular higher frequency. With this, I'd like to stop my discussion. Please help to like and subscribe. Once again, sincere thanks for your strong support. See you guys.